Hi guys, this is A2 Chemistry, Transition Elements, and we are looking at Stability Constant or K step. Question 1. The transition element ions often exist as hexa-aqua complexes in aqueous solution. The reactions which involve ligand exchange are reversible, and the reaction is shown. Write an expression for the stability constant for this equilibrium, give its unit. So, on the product side, we've got 4 moles of water, which are not included in the expression of the equilibrium constant. So the numerator would be the ion CuNH3 four times and H2O twice. This has a molar ratio of 1, so it will be raised to the power of 1 divided by, we would have CuH2O 6 times 2 positive raised to the power of 1 multiplied by ammonia. Since there are 4 moles of ammonia, so this would be raised to the power of 4. Now, we have a concentration in the numerator and 5 concentration in the denominator. One of them will cancel out. We are left with 1 upon mole per dm cube raised to the power of 4. So bringing this up into the numerator, we will end up with the units of mole power minus 4 and dm power plus 12. Next, the numerical value for K step for this equilibrium at 298 kelvins is 1.20 into 10 to the power of 13. Explain how this value relates to the relative stabilities of the two complex ions. So, since the K stab is very large, the forward reaction is favored and a large quantity of CuNH3 four times H2O twice 2 positive ion would be present at equilibrium as it is very stable. Now, this stability is in comparison to the complex present in the reactant, which is copper surrounded by 6 water. So, since a high stability constant value is present for the copper ion with 4 ammonia and 2 water molecules as ligand, it would be present in a larger quantity. That means the equilibrium will be favored in the forward direction. Question 2. Cadmium ions form complexes with primary amines and with 1,2-diaminoethane, and both these equilibriums have been written. Write an expression for the stability constant for equilibrium 1 and state its units. So, equilibrium 1 has a single product which will go into the numerator, that would be CD. We have CH3 NH2 taken 4 times with a 2 positive charge, and since the molar ratio is 1, so it would be raised to the power of 1 divided by, we've got 1 mole of cadmium ion, so Cd2 positive raised to the power of 1 multiplied by 4 moles of CH3 NH2. So it would be concentration of CH3 NH2 raised to the power of 4. For the units, we've got 1 mole of concentration in the numerator and 5 moles in the denominator. So 1 mole will cancel out. We are left with 1 upon mole per dm cube raised to the power of 4. Bringing these up into the numerator, the units would be mole raised to the power of minus 4, dm raised to the power of plus 12. Question 3. Hexa, aqua, iron 3 ions are pale violet. They form a colorless complex with fluoride ions, equilibrium 1, and a deep red complex with thiocyanate ions, equilibrium 2. So, based on the K star values, equilibrium 1 is more stable than equilibrium 2, which means the hexa aqua iron 3 ions converting into the ones with the fluoride ion is more stable than the ones with the thiocyanate ions present. So, predict and explain the sequence of color changes you would observe in each of the following experiments. A few drops of KSCN are added to Fe3 plus aqueous. So, in this case, the color would change from violet to deep red, and it says followed by a few drops of KF. So if KF is added to the deep red color, then the deep red color would turn colorless because we are going from a less stable ion to a more stable ion, which would be preferred. So the color change would be deep red to colorless. This is due to ligand exchange in order to form a more stable complex. Next, a few drops of KF are added to 5 cm cube of Fe3 plus aqueous. So here the color would change from violet to colorless, but followed by a few drops of KSCN. So the complex formed with fluoride is more stable than the complex that can form with the thiocyanate ions. So fluoride being replaced by thiocyanate ions will not occur. So we will write solution remains colorless. This is because the more stable ion was formed in the first step. What type of reaction is occurring during experiments in one? So since ligands are being replaced, so the type of reaction is known as ligand substitution reaction. Question 4. Copper also forms the complex ion CuNH3 twice H2O4 times 2 positive and CuEnH2O4 2 positive, where En is the bidentate ligand ethane 1,2-diamine. Two equilibriums are shown. What is meant by the term bidentate ligand? So it is a molecule or ion having two lone pairs of electrons present, which form two dative covalent bonds with the transition metal ion. The table lists the values of stability constant for these two complexes. Okay, this value is higher than the first value. What do these stability constant values tell us about the relative positions of equilibria 1 and 2? So, since the value for equilibrium 2 is higher, it tells us that equilibrium 2 lies more towards the right as the complex formed is more stable as shown by the higher K stab value. Question 5. The reaction of NiH2O6 2 positive with aqueous ammonia produces the complex NiNH3 6 2 positive. And the equilibrium is given. Write an expression for the K step of NiNH6. So, since water molecules are present in the product, they will not be included in the expression of the equilibrium constant. So, the numerator would have NiNH3 6 times 2 positive raised to the power of 1 because there is only 1 mole of it present, divided by concentration of NiH2O6 2 positive raised to the power of 1 multiplied by concentration of ammonia raised to the power of 6, since 6 moles of ammonia are present in the given equilibrium. And if we were to find out the units of this K stab expression, we would have 1 over mole per dm cube raised to the power of 6, since 1 mole of concentration from the numerator and denominator gets cancelled out. So the units for this case tab would be mole power minus 6 dm power plus 18. Next, NiH2O6 2 positive also reacts with En to form NiEn thrice 2 positive. The value of the stability constant for the two complexes are shown. So with 6 ammonia, the value is 4.8 10 power 7, and with 3 En, it is 2 into 10 above 18. So this is much higher than the one with 6 ammonia ligands. A solution containing equal number of moles of ammonia and En is added to NiH2O6 2 positive. State which complex is produced in large amount and explain your answer. So NiEn thrice 2 positive would be produced in a large quantity because it has got a higher K stab value, meaning that it is a more stable complex. Question 6. Iron 3 forms complexes in separate reaction with both SCN and Cl negative ions. So the equilibria are shown. Write the expression for the stability constant for these two equilibria. Include units in your answers. So for the first one, it would be FeSCN 2 positive concentration raised to the power of 1 divided by concentration of Fe3 plus raised to the power of 1 multiplied by concentration of SCN minus raised to the power of 1. So since we have a single concentration in the numerator and two concentrations in the denominator, we end up with the unit of 1 upon mole per dm cube, which would be mole raised to the power of minus 1 and dm raised to the power of plus 3 when brought into the numerator. For the second equilibrium, we've got concentration of FeCl4 negative raised to the power of 1 divided by concentration of Fe3 plus raised to the power of 1 multiplied by concentration of Cl negative raised to the power of 4, since there are 4 moles of chloride ions present. So the units would be 1 over mole per dm cube raised to the power of 4. Since 1 mole per dm cube in the numerator and denominator gets cancelled out, so bringing these units into the numerator side, we end up with mole power minus 4 and dm power plus 12. Next, an equilibrium can be set up between these two complexes as shown in equilibrium 3. So the equilibrium is shown. Write an expression for KEQ3 in terms of K step 1 and K step 2. So in equilibrium 3, the SCN ions are present on the reactant side, which means that this equilibrium will be proceeding in the forward direction. And we have got FeCl4 negative ions present on the reactant side, which are products of equilibrium 2. That means equilibrium 2 will be proceeding in the backward direction. So the stability constant value for the forward direction is represented by K step 1, and for the backward reaction it is represented by 1 over K step 2, because the forward reaction is K step 1, so the backward reaction has to be the inverse of that. So when we put these two together, we end up with the KEQ3 value of K step 1 upon K step 2, and that is how we would calculate the KEQ3 for the said equilibrium. Next, the number or numerical values for the stability constants are shown. Calculate the value of K equal to 3, stating its units. So we divide 1.4 into 10 to the power of 2 by 8.0 into 10 to the power of minus 2. We end up with a numerical value of 1750. And in order to calculate the units, we divide mole per dm cube, actually mole minus 1 dm plus 3 by mole power minus 4 and dm power plus 12, and we are left with 1 upon mole power minus 3 dm power plus 9. And when we bring this into the numerator side, these are converted into mole cube and dm power minus 9. Question 7. Copper forms complexes with ammonia and En according to equilibria 1 and 2. Write the expression for the stability constants K step 1 and K step 2 for equilibria 1 and 2. So the K step values would be products upon reactant. So for equilibrium 1, it would be concentration of CuNH3 4 times 2 positive raised to the power of 1 divided by concentration of Cu2 plus raised to the power of 1 multiplied by concentration of ammonia raised to the power of 4. So the units would be 1 upon mole per dm cube raised to the power of 4, since a mole per dm cube in the numerator and denominator gets cancelled out. So this turns out to be mole power minus 4 dm power plus 12 when we bring the units into the numerator. For equilibrium 2, the expression would be concentration of Cu En twice 2 positive raised to the power of 1 divided by concentration of Cu2 plus raised to the power of 1 multiplied by concentration of En raised to the power of 2. So the units would be 1 upon mole per dm cube squared, because 1 mole per dm cube in the numerator and denominator gets cancelled out. And when we bring this into the numerator side, we end up with units of mole power minus 2 and dm power plus 6. An equilibrium is set up when both E and ammonia ligands are added to a solution containing Cu2 positive aqueous as shown in equilibrium 3. So comparing equilibrium 3 to equilibriums 1 and 2, we've got CuNH3 four times on the reactant side, which is the product in equilibrium 1. That means equilibrium 1 is moving in the backward direction, which means that the K step value for equilibrium 1 in the backward direction would be 1 over K step 1. And we have equilibrium 2 moving in the forward direction because En are present as reactants in equilibrium 3. So this would be K step 2, and when we put these two together we end up with an KEQ value equaling to K stab 2 upon K stab 1, and that is how we will calculate KEQ 3. The numerical values for these stability constants are shown. So K step 1 and K step 2 are given. Calculate the value of KEQ3 stating its units. So we would calculate K step 2 upon 1. So this would be 5.3 into 10 to the power of 19 divided by 1.2 into 10 to the power of 13. We end up with a numerical value of 4.42 into 10 to the power of 6. And the units would be mole power minus 2 dm power plus 6 divided by mole power minus 4 dm power plus 12. So we end up with 1 upon mole power minus 2 dm power plus 6, which when brought into the numerator side becomes mole square dm power minus 6. Question 8. The table shows numerical values of the stability constants for the following equilibrium, where M can be one of the metal ions listed and L one of the ligands which replaces one water molecule. So the equilibrium is given in which one ligand replaces one water molecule. What is meant by the term stability constant? So stability constant, it is an equilibrium constant for the formation of complex ions in solution. That is the definition of the stability constant. Next, use the data in the table to predict the formula of the complex formed in the greatest amount when a solution containing equal concentration of both F negative and SCN negative ions is added to Fe3 plus. So Fe3 plus with F negative has a stability constant of 110 power 6, and with SCN negative is 910 power 2. So with fluoride it is more stable. So that is the one that will form. So the ion form would be Fe H2O 5 times with a fluoride ion present, and the overall charge would be plus 3 and minus 1 for fluoride, so overall charge will be plus 2. For the second part of this question, a solution containing equal concentration of both Fe3 plus and Hg2 plus ions is added to chloride ions. So if we have Cl negative ions attaching to iron 3 ions, the stability constant is 2.5 10 power 1, and with mercury it is 5 10 power 6. So the mercury one is more stable. Therefore, we end up with the complex ion Hg H2O 5 times and Cl. So Hg has a charge of plus 2 and Cl has a charge of minus 1. So overall charge of the complex would be positive 1. Ethane dioate ions are bidentate ligands. The abbreviation ED2 minus can be used to represent ethane dioate ions. The complex FeED2Cl twice 3 negative can be formed according to the equation shown. Write the expression for the equilibrium constant K stab and state its units. So water will not be included in the expression of the stability constant. So the numerator will have FeED twice, Cl twice, 3 negative, concentration raised to the power of 1 divided by FeH2O 4 times, Cl twice, positive raised to the power of 1 multiplied by Ed2 minus raised to the power of 2. So since 1 mole per dm cube gets cancelled out from the numerator and denominator, the units we are left with are 1 upon mole per dm cube squared, which when brought into the numerator becomes mole power minus 2 and dm power plus 6. Question 9. EDTA4 negative is a polydentate ligand. When a solution of EDTA4 negative is added to a solution containing CuH2O6 2 positive, a new complex is formed. The formula of this complex is CuEDTA whole 2 negative. Name the type of reaction occurring here. So this type of reaction is known as ligand substitution reaction, because water molecules are replaced by EDTA. Write an expression for the stability constant of CuEDTA2 minus in this reaction. So the expression of K stab would be equal to CuEDTA charge of 2 negative raised to the power of 1 concentration divided by concentration of CuH2O6 2 positive concentration raised to the power of 1 multiplied by concentration of EDTA4 negative raised to the power of 1. And if we were to include units, the units would be 1 upon mole per dm cube, because 1 mole per dm cube in the numerator and denominator gets cancelled out. So the units for the K step would be mole power minus 1 dm power plus 3. And also to note here, 6 water molecules would have been part of the products, but water is not included in the expression of the equilibrium constant. Next, the numerical value of K step of CuEDTA2 minus is 6.3 10 power 19. It's a large value at 298 Kelvin. State what this tells us about the CuEDTA2 minus complex ion. It tells us that this complex is much more stable than CuH2O 6 times whole 2 positive. That is why its formation is preferred and it has a large value for K stab.